Welcome back to the deep dive. We're looking at the Mastering Cambridge O-Level Physics series.
And based strictly on the official new syllabus.
Yeah, so by showing the syllabus on screen, which they do.
Exactly.
Specifically, topic 4.2 from the Cambridge O-Level syllabus.
Slide 2 in our deck introduces us to the players, positive and negative.
The fundamental duality of the universe, right there. And we measure this stuff in coulombs, which is represented by a big capital C. Now, most people know the golden rule of interaction here. It's kind of the oldest relationship cliche in the book.
Opposites attract.
And likes repel. If you have two positive charges, they will fight to get away from each other. A positive and a negative. They will rush together. That force, that constant push and pull, is the engine that drives everything else we're going to talk about.
But here's something I found interesting on slide 3. It talks about charging by friction. We've all done this. Rubbing a balloon on your hair to make it stick to a wall, or shuffling across a carpet to zap your sibling. But there is this massive, bold, underlined warning on this slide. Key rule.
Yes, and this is probably the most common misconception in basic physics. The rule is only negative electrons move. Positive protons stay put.
Which feels a little counterintuitive to me. I mean, if I rub a plastic rod with a cloth and the rod becomes positive,
yeah,
my brain wants to assume I added positive charge to it, like spreading peanut butter on toast or something.
I get that logic, I really do, but physically, it's impossible in this context. Think about the architecture of an atom. The protons are these heavyweights locked deep inside the nucleus. They are anchored. They aren't going anywhere unless you're splitting atoms, which is a whole different deep dive.
Right. Let's avoid nuclear fission for today.
Good plan. So the protons are locked in the center, but the electrons, they are these tiny, flighty particles buzzing around the outside. They're on the periphery. They are very easy to scrape off.
So it's a game of subtraction then.
Precisely. If that plastic rod becomes positive, it's not because it gained protons, it's because the cloth stole its electrons. The cloth then becomes negative because it gained those stolen electrons. It's purely a transfer of the negative particle.
So whenever you talk about static electricity, we're really just talking about moving electrons around. Okay, so we've got these charges, but they don't need to physically touch to affect each other, do they? Slide 4 brings up the concept of the electric field.
Right. Think of the electric field as a kind of spider web. A charge sits in the middle and extends this invisible region of influence all around itself. If another charge wanders into that web, it feels a force. It gets pushed or pulled, even in what looks like empty space.
But how do we map invisible webs? The diagrams on slide 5 show these arrows radiating out from a central sphere. It looks a bit like a starburst or a porcupine.
We map it using a convention. We ask a hypothetical question. If I dropped a tiny positive test charge right here, which way would it run? And since positive repels positive, if your main object is positive, that little test charge is going to run away. So the arrows on a positive sphere point outward.
And if the main object is negative,
then that positive test charge would be attracted to it. So the arrows would point inward toward the center.
That makes sense. Now, there's one specific pattern on this slide I want to touch on because it looks so different. The parallel plates diagram. It's a positive plate on top, a negative plate on the bottom, and the lines are perfectly straight, running top to bottom.
Right.
Like prism bars.
This is a crucial concept. Those parallel lines represent what we call a uniform field. If you are a charge anywhere inside that gap, whether you're near the top, the bottom, or dead center, the force you feel is exactly the same. It's a perfectly controlled environment.
Okay, so we have the stuff, the charge, and the influence, the field. But static electricity is, well, a bit boring. It just sits there. We want power. We want to screen movies. We need to get this stuff moving. Which brings us to the highway. Conductors versus insulators.
Or, as I like to call them, the open road versus the roadblock.
Slide 6 contrasts materials like copper and aluminum against plastic and glass. We all know copper conducts electricity and glass doesn't. But why? Is it just about the material being dense or something?
It's not about density, it's all about freedom. This goes right back to our electron model. In a metal like copper, the atoms form a lattice of structure, but they let their outer electrons wander freely.
The slide calls them free E electrons.
Right. It's often described as a sea of electrons. They aren't shackled to any single parent atom. They can just drift through the metal structure like a gas. That's why if you apply a push, they all flow instantly. They're ready to move.
Whereas in plastic,
in an insulator like plastic or glass, the electrons are on a very short leash. They are held tightly to their specific atoms. You can push them, and they just wiggle in place. They can't let go. And if the electrons can't move, you can't have a flow. No flow, no current.
And current is our next big character. Slide 7 defines it as the charge passing a point per unit time.
And this is where we get our first big formula. I equals Q over T. Current, which is I, is the amount of charge, Q, divided by time, T.
And the unit is amperes, or amps. We see that on plugs all the time, 2.1 amps.
Exactly. And to give you a sense of scale, 1 amp is literally 1 coulomb of charge flowing past a point every single second. And 1 coulomb is a staggering number of electrons. It's about 6 billion of them.
That is a lot of traffic.
That's a massive amount of traffic.
The visual on this slide is helpful too. It shows a tube, basically a wire, and you see these little electrons drifting from left to right across a dotted line. It makes it really clear that current isn't just energy floating around, it's physical stuff moving past a checkpoint.
But hold on, look at slide 8. Do you see the problem? This is where things get a little messy.
Oh, I see it. The direction dilemma. This is actually kind of funny. The diagram shows a circuit with a battery and a loop of wire. There are arrows labeled electron flow going one way, and then arrows labeled conventional current going the exact opposite way.
Welcome to the biggest oops in scientific history.
How does that even happen? We just spent 10 minutes establishing that electrons are the things that are moving, and electrons are negative. So why on earth does current flow the other way?
History. It's all Benjamin Franklin's fault, essentially. Early scientists knew electricity was some kind of fluid. They knew there were 2 types of charge. Franklin just guessed that the positive fluid was the one doing the moving, so he drew the arrows flowing from positive to negative.
Guess.
He had a 50 shot, and he guessed wrong. He didn't know electrons even existed yet. By the time we discovered the electron over 100 years later and realized, wait, it's actually the negative stuff moving from negative to positive. Well, it was too late.
Too late. Can't they just update the books?
All the textbooks were written, all the formulas were set, all the engineering diagrams for the telegraph and the early power grids were drawn, so the scientific community made a pragmatic decision. We basically agreed to a global conspiracy for the sake of paperwork.
So we just kept it.
We kept it. We call it conventional current. It flows from positive to negative. That is what you will see on every diagram, every schematic, and in every exam. Unless a question specifically asks for electron flow, you always assume the Franklin direction, positive to negative.
That is wild. We literally just agreed to pretend for the sake of consistency.
Science is a human endeavor, after all. We make mistakes, and sometimes we just patch them up and keep going.
Okay, before we leave current, the slide briefly mentions AC versus DC.
Right. Direct current, or DC, is what batteries produce. The river flows one way, always. Alternating current, AC, is what comes out of your wall socket. The electrons just vibrate back and forth, changing direction 50 or 60 times a second. But for the O-level physics we're looking at today, we're mostly living in a direct current world. Simple loops, one direction.
Okay, so we have the charge the vehicles, and we have the current, the traffic flow. But traffic doesn't move without a reason. Water doesn't flow uphill. It needs a push.
Enter voltage.
This is where I think people get stuck. I know I used to. Slides 9 and 10 break this down into 2 different concepts, EMF and potential difference.
It is confusing. I mean, they are both measured in volts with a V. If you use a multimeter, it doesn't say this is EMF or this is PD. It just gives you a number. But physically, they're opposites.
So how do we distinguish them?
Think of the circuit like a water heating system in a building. You need a pump to pressurize the water and send it up to the top floor. That pump is the EMF, the electromotive force.
Slide 9 defines EMF as the electrical work done by a source in moving a unit charge around a complete circuit.
The key word there is source. Batteries, generators, solar cells. EMF is the energy. It's taking chemical energy in a battery or mechanical energy in a generator and turning it into electrical push. It's giving the electrons their lunch money for the journey.
I like that. So EMF is the paycheck. It's the energy given to the charge. Then what is potential difference, or PD, on slide 10?
Potential difference is the energy spent. The definition is the work done by a unit charge passing through a component.
So when the electrons hit a light bulb or a resistor,
They have to pay up. They transfer that electrical energy into light or heat. They lose pressure. The potential difference measures that drop. It's the difference in energy from the entrance of the bulb to the exit of the bulb.
so EMF is the pump, the input. Potential difference is the turbine, the output.
Exactly. One creates the electrical potential, the other uses it up. And physically, that's why the slide reminds us to connect a voltmeter in parallel.
Right. Why is that placement so important?
Because you're measuring a difference. If you want to know how much taller I am than you, I have to stand next to you, right? If you want to know how much energy a light bulb used, you have to measure the voltage on one side and the voltage on the other side. You have to hug the component with the meter.
And both of these are measuring joules per coulomb.
Yes, which is a really helpful way to think about what a volt. 1 volt just means 1 joule of energy carried by every single coulomb of charge. It's basically the value of the cargo each electron is carrying.
So we've got the push voltage and the flow current. Now we have to talk about the villain of the story.
Yeah.
Or maybe just the regulator. Slide 11, resistance.
The obstacle.
The definition is simple. The opposition to the flow of current. And we get the formula R equals V over I.
which tells us that resistance is a ratio. It asks the question, how much push V do I need to apply to get a certain amount of flow? If I have to push really hard to get just a trickle of current, that's high resistance.
The visual analogy on the slide is a pipe that suddenly gets pinched and narrow.
That constriction is the resistance. Imagine you're driving down a 5-lane highway, and suddenly it merges down to 1 lane for construction. What happens?
Oh, traffic slows way down, bumper to bumper.
Exactly. And there's friction, drivers get angry. In the wire, that friction is literal. As electrons try to squeeze through a component that resists them, they are colliding with the atoms of the material. Those collisions transfer energy. The wire gets hot.
So that heat isn't an accident.
No, it's the direct result of resistance. That's why your laptop charger warms up. It's the feeling of electrical friction.
And we can actually measure this in the lab. Slide 12 shows a circuit diagram. It looks like a classic school experiment.
It's the standard test circuit. You have a battery, a switch, and the component you're testing. Let's say it's a piece of wire. Now watch where the meters go. You put an ammeter in series right in the main line to count the traffic, the current.
Because you want to count every single car that goes by.
Right. And you put a voltmeter in parallel across the component to measure the pressure drop, the PD.
And you just take those two numbers, divide V by I, and you have your resistance in ohms.
Simple as that. But, and there is always a but in physics, resistance isn't a fixed number for everything. It depends on the architecture of the object.
Slide 13 breaks this down. Factors affecting resistance. It uses a wire as the example.
Let's go back to our analogy of you moving through a space. Imagine you have to crawl through a ventilation duct. That's you, the electron.
Okay, I'm in the duct. It's dark. I'm trolling.
Factor 1, length. The slide says it's directly proportional.
Longer wire equals more resistant. That makes sense. If the duct is 10 miles long, I'm going to be exhausted. I'm going to bump my knees way more often than if it was 10 feet long.
Exactly. More length means more atoms to bump into, more collisions, higher resistance.
And factor 2, cross-sectional area. The thickness of the wire. This is inversely proportional.
Meaning a thicker wire equals less resistance.
Because it's a wider hallway?
Precisely. If the duct is wide, you have more room to move. You aren't scraping your shoulders against the sides. In a wire, a larger cross-section means more lanes for the electrons to travel.
So if I want to get power from point A to point B with the least amount of loss-like transmitting power across the city, I want a short, fat wire.
Correct. Thick cables are essential for power lines to keep resistance low. But if I want to create a lot of heat or limit the current like inside a toaster or a space heater, I want a long, thin wire. That creates the bottleneck that generates the heat.
Now, we've been treating this relationship between voltage and current as a law, and slide 14 calls it exactly that, Ohm's law.
The golden rule of circuits. It states that current is directly proportional to potential difference. So if you double the push, you get double the flow. Triple the push, you get triple the flow.
The graph on the slide shows this beautiful straight diagonal line starting from 0.
That straight line is what we call ohmic behavior. It means the resistance is constant. It doesn't matter if you put 2 volts or 20 volts through it. The difficulty of getting through stays the same.
But I'm looking at the fine print on the slide. There's a disclaimer. Provided temperature remains constant.
Ah, the disclaimer. That's where the real world ruins our perfect math. Why does the temperature matter?
Well, slide 15 introduces non-ohmic components, the rule breakers.
Let's look at the graph for the filament lamp, an old school incandescent light bulb. It starts straight, but then it curves over. It gets flatter as you go to the right.
So as the voltage goes up, the current stops keeping up. It's like it's hitting a wall. The resistance is increasing.
Yes. Think about what's happening inside that filament. It's getting incredibly hot. That's why it glows white hot. And when atoms get hot, they vibrate. They wiggle violently.
So for the electrons trying to get through.
Imagine trying to run down a hallway. If everyone is standing still, you can weave through them. That's a cold wire. But now imagine everyone in the hallway starts jumping up and down and flailing their arms like they're in a mosh pit.
That's a hot wire.
Exactly. It becomes much, much harder to pass without colliding. The hotter the filament gets, the more the atoms vibrate, the more collisions you have, and the higher the resistance goes.
So it's a self-limiting system in a way. The harder you push, the harder it pushes back.
Exactly. It creates a curve on the graph. It is definitely not ohmic.
And then there's the other weird one on this slide, the diode. This graph is just bizarre. It's flat at 0 on the left, and then it suddenly shoots straight up on the right.
The diode is the one-way valve, or the check valve of electronics. The slide says it conducts in one direction only.
So if you try to push current backwards, what the graph calls reverse bias, it just says no.
Zero flow. Infinite resistance. It blocks the traffic completely. But if you push in the correct direction, forward bias, once you overcome a tiny threshold voltage, the gate swings wide open and resistance drops to almost nothing. The current shoots up.
It's basically a digital switch, on or off, and direction matter.
And that simple property controlling the direction of flow is the fundamental building block of logic, of computing, and essentially the entire digital age. But that's a deep dive for another day.
So, looking back at our mission, we've decoded the stack. We started with charge-o-static specs of positive and negative, realizing only the electrons do the moving.
We separated them to create potential. We gave them a path conductors and watched them flow as current.
We saw how voltage acts as the pump to push them, giving them energy, and how resistance acts as the pipe that squeezes them, creating heat.
And we realized that this interplay charge, current, voltage, resistance, isn't just textbook theory. It's the hidden traffic system running every single device you own.
When your phone heats up in your hand.
That's resistance converting electrical work into thermal energy.
When your battery dies.
Your EMF source has run out of chemical potential to push the charges. The pump has stopped.
It connects everything. It's really satisfying to see how these four concepts just lock together. But before we sign off, I have a question based on that filament lamp slide.
Go for it.
We saw that resistance creates heat, right? The friction of the electrons.
Right.
But we also saw that heat increases resistance. The mosh pit effect.
A feedback loop.
So here's my thought for you, the listener, to take away. If resistance makes things hot, and getting hot adds more resistance, which makes it even hotter, why doesn't every electronic device we own enter a thermal death spiral and melt the moment we turn it on?
That is the question that keeps thermal engineers awake at night.
Something to chew on next time you hear your laptop fan screaming for help. Thanks for listening to this deep dive into the wires.
Safe travels.
See you next time.